Good morning. Welcome to Krishna's classroom. Last time we started with a measure space x m mu and then defined and considered all the complex valued measurable functions on x with the norm fp less than infinity, and norm f it is actually a semi-norm. And we have seen that norm fp is a what you call a semi-norm on LP, although we call it norm at the moment. So it's a it's a wrong nomenclature because why we call it semi-norm? It satisfies, that is, it satisfies all the properties of a norm. That means length, except that norm of f equal to 0 may not imply degree 0. In fact, what it does is, all that we can say is that f is equal to 0 almost everywhere on. Now, this is the significant departure from being a, okay, and that's a shortcoming really, because to work on LP mu as we have defined, and with this particular choice of the possible length function, norm p, it is difficult to get a normed linear space. Therefore, it is not a normed linear space. In fact, we call it a semi-normed space. Okay. So that is the first observation that we made when we have made remarks about it. Now, what we want is, for our purpose, a normed linear space. Okay. And you know that when you have a norm, automatically it induces a metric on LP. So a LP mu defined by this is the definition: dp f now you see that this is well defined. This is well defined because f minus t is an element of LP, and on which norm p is defined, and you call this, so it actually gives defines a non-negative real valued function on LP cross LP, okay, with all the properties of a metric except one. Okay, so what is that we can prove? Okay, note that Or we'll do this. Metric. It satisfies all properties of a metric other than dp f identically equal to G. This is important. Okay. Now that's the definition of a pseudo metric. So it's a metric except for one property, namely the distance from F to G may be, equal to 0 even when F is not equal to G sometimes. Okay. So we cannot assert that dpfg equal to 0 implies fg equal to 0. That is f is equal to G. This is the important aspect of dp. Okay, so we shall prove this. So first of all, dp is zero. How do you prove this? So this is the first one. So dp is this is well defined, and you know that this is greater than or equal to 0. That's the first thing. The second property that you have is this. See, yeah. dpfg equal to 0 if and only f minus g equal to 0, and that implies f equal to g almost f equal to g almost every. We cannot say that we cannot say that F is equal to G. Or F and G may differ on a set of measure 0. Okay, that is the problem. This you can prove. F is equal to G almost everywhere or X. So here we make a remark. F may not be identical with G. This is the remark. Now what are the other properties of the metric? That is easy to verify. Now the third property is but that is obvious. So you have dp which is equal to that is okay. And the fourth property is the triangular inequality. So we have to LP. This is the triangular inequality. Now this is easy to prove because you have dp all routine things. Which in turn is less than or equal to, we are using triangular inequality. Which is equal to this is true for every LP mu. So you see that LP mu with dp we have defined. So dp is a metric space, just falls short of being a metric space in the sense that the second statement I have made is not valid. That means you cannot say that dpfg equal to 0 implies f equal to g. Of course, if f is equal to g, obviously, so you have, okay. So we shall just use that, make a statement about it. So dp actually falls short of giving a metric on LP. So this completes the proof. Of the requirements of to be a metric. This is significant. Okay, let us all that you need is, all that we can say is that we designate dp a pseudo matrix and LP this is just the problem that we had been encountering all along. So we fail to get a metric space. So how to get a metric space? Okay, only if you get a metric space, you have a topological space. Okay, so that you can do analysis. So how to get a metric space from this? Okay, this is our task. This is the problem. That is the problem that we are encountering. Now, in this context, it's nice to recall how we worked to construct rational numbers from fractions. So, recall what we did. See, in this case, what was the problem that we were facing? The same rational number may be represented by different fractions. The same rational number may be represented by for example, etc. represent the same rational number. Usually designated as okay. What is the relation between these numbers? See that see that 1 by 2 equal to 2 by 4 because 4 into 1 equal to 2 into. This is the reason. Similarly, 1 by 2 equal to 3 by 6 means 6 into 1 equal to 3 into 2. So this is the reason. Therefore, we use the fact that we say that see, we said P by Q is related to P1 by Q1 or represents the same fraction if and only if PQ1 equal to P1, because we are assuming Q and Q1 are not equal to 0. Okay. So in short, we are taking the set of all natural numbers and then defining a relation in that class. Set of all natural numbers, and on n cross n, take Z and defined a relation on Z is the set of all integers on this is because you had this condition that the whatever is appearing in the denominator, which appears in the second place, is not equal to 0. Okay, by it is not equal to 0. Okay. PQ1 equal to P1. So this was the relation that we defined. Now what we observed is that this we designated by P is, or what you call P by Q is related to P1. Q1. That is the designation that we get. That is the relation. Okay. Now, what is that you can say? This, in fact, defines a partition on. This is this relation I don't want to go to the proof of this, because what we want to do, the first thing is the second property is that this is what you call reflexivity. PQ related to P1 Q1 if and only if this is what you call symmetry. Zero. The third property is that is the symmetry related to P1 Q1 and P1 Q1 is related to P2 Q2 implies PQ is related to so this is what you call transitivity. So this relation actually is an equivalence relation. This is quite nice to visualize this also. Okay, what is happening? So PQ is transitive, right? Equivalence relation on and therefore induces a partition of okay. Now this is the usual property. If you have a set X on which you can define a relation which is an equivalence relation, then it induces a partition. What do we mean by that? see, that particular set is written as the disjoint union of subsets, each subset being a set of points which are mutually related. Okay, mutually related. Now this is the thing. Suppose I denote this by, because since I am using x elsewhere, let me denote it by y. Y is equal to z cross this, for instance. Okay. Now you have on y you have a equivalence relation. Then what you have is this y is written as the union of disjoint union of 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 subsets of y. Okay, with the property that if P belongs to P and Q are 2 points, then P is related to. But if P1 is here and Q1 is here, then P1 is not equal to, not related to Q1. Okay, so all these elements here are related to one another. All these elements here are related to one another. But if you take an element from here and an element from here, they are not related. For instance, in the present scenario of the example, we see that 1 by 2 is not related to 1 by 2. Why? Because 3 into 1 not equal to. Okay, so that is the particular case that we. And now what we do, so we have now partitioned the set into blocks consisting of mutually related elements. Okay, so that defines a new set. Okay, so we define a new set here. We define a new set which are the elements of this. The elements of this are the set of all y, or with the property that, okay, we'll define this. We define x is related to y. Okay, where this is an equivalence relation. We have so this is what we do, and then write y tilde as the set of all set of all equivalence classes of this type. So each block now is an element of y tilde. That's the meaning. Okay, let us use this. You can use here. Why? This also can be written as possibly written as x. Then y is related to x, whereas y is not related to z. This is the scenario. Okay. So we took all the fractions and on that we defined an equivalence relation, and that induced a partition. And each partition block we considered as the rational number. Okay, so that is the definition of the rational, right? And I'll just give a pictorial view of this. Just I am digressing probably, but may be worthwhile for the students who are working on this. Now this is the first stage where one comes across this technique, and which is generally used in constructing equivalence classes and so on. Now let us give a pictorial view. You take this is z cross z, out of which we will just mark out this point. Okay, from this. So we are taking only or I'll put it this way, I'll take this as z and this as, and then connect like this. Now you take 2 points whose coordinate is PQ, where Q is not equal to 0. So you take PQ with Q not equal to 0, but P comma Q belonging to Z. Okay. Now you see you can draw a line to this point. Okay. And you take all the points on this line whose coordinates are integers. Okay, right? So we take L, the equation line, set of points strictly speaking the half line. Originating from here. So this point is not there. Okay. Then what do you get? These points are by the relation defined by okay. Now the collection of these points a rational number, the rational number PQ, designated by PQ. Actually, what you do is you take out the common denominator or common factor between P and Q. You remove. This is what is happening. Is so you take 1 by 2. 1 by 2 consists of the entire set of fractions, namely 2 by 4, 3 by 6, etc. etc. Okay, or minus 1 by 2 consists of minus 2 by 4, minus 3 by 6, etc. etc. So you get such blocks. Okay, and this is the geometry of that. You get this line and you get points with P1, Q1. So these two are on this, and the whole block represents this. And then the story is that if you are familiar with all this, you will see that you can define addition and multiplication without any problem on this class. Okay, and this class is what you call the set of rational numbers. This is how you build rational numbers from from integers. Okay, so let me just wind it up. Let me just stop it there, and we come back to our problem. So now we return to the problem. We do a similar process. The first thing that we observe is that okay, so consider for any specific value of P. Okay. Now on this, P equal to 0. That means F may not be equal to, I said earlier that this may not imply F is equal to G. All that you can say is that F and G are equal almost everywhere. Okay, so you take such whole class of functions from this, right? Now we claim so what do we have to do? We have to F is F equal to 0. The second property is so you see that this means equal to 0, and that implies equal to 0. Therefore, this is what you call reflexivity, and this is what you call symmetry. Now the third property is F is related to G and G is related to H. How do we prove this? I mean, that's easy to see. You have a so what we claim is this. This is true because and this is equal to 0, which implies so this is transitivity. Therefore, on LP, and this is, see, equivalently F minus GP is the same as dP. Therefore, on LP, dP relation and hence it's a partition. This is the relation. Hence, on LP, induces a partition. A partition. Consisting of the equivalence classes. Now we shall write as the block F belonging to LP mu G is related to so you take all the G in LP mu which is related. Okay. Now then you have immediately two things. Then we have immediately the following properties. What are they? Related to F1. Okay. And this is if and only relation. So it's a very strong relation. Okay. So that this so we now designate by the equivalent the blocks F with the property that F belongs to these are now the elements of the new class and this is our definition. Okay. Now we define on this dp for every F This is the definition. Then we prove the theorem. It is more than a pseudo matrix space. It's quite easy to prove. Why? That follows from the definition. Okay, from the definition. The second property is mod G. Sorry, this block F equal to block G. Now, what do we get from this? This is equal to norm of F minus G equal to P. I mean F minus G P. Okay, and this is equal to 0 if and only if F equal to G almost everywhere on X. Okay, and that is the equivalence relation. Okay, mod G. I mean, not mod, I mean the block F is equal to block G. So that is the crucial thing that you have to prove. Now the other properties, this I leave it to you. All that you need is write this is norm, and this is equal to, and they are equal. Okay, so the fourth property is and that's quite easy to prove because this stands for So from this it immediately follows that. So you see that now the LP tilde DP is a metric space. Okay, so what we have done is from a pseudo metric space, we have constructed a metric space. Okay, so this is the usual art of doing it. We have seen in two circumstances, and the guidance that we got is from this, and of course the most general form in which you can write this property, that is, if you have X on which you have a pseudometric D, then you can construct a a metric space from it by using this equilattice class approach. Okay, right? So I think this is a stage where we can stop today, and our next task will be to show that LP mu is LP tilde mu is a normed linear space. Okay, right? It's not only a metric space, it's also a normed linear space, and this metric essentially comes from that norm. Okay, one could prove it the other way around. First, you prove that this is a normed linear space, and then get the metric space out of it, or the other way around. It's all the same. Okay, so we will do that in our next lecture, because that involves slightly more or small complexities. I mean, here also we have this kind of question: is F minus G is in LP epsilon? I mean, that is there. The way in which we have defined it is there. So I think I have a tilde missing here that I have introduced. Okay, thank you very much. So we will prove that LP tilde norm P norm is a when we prove that it is a norm. That's our next task. So thank you very much.